everywhere. Okay? So we are talking about damped or harmonically excited damped systems. Okay, that's what we were talking about. So this was the equation of motion, right? We set it up in this form. And as we said, this equation has two solutions: homogeneous particular solution, particular being the steady state, which is what we want to focus on. We said that using, of course, the classical approach, the solution will be of this form. Okay? So we have two unknowns that we need to find. In order to find them, just substitute this solution back into that equation. Okay? And you end up with terms that are the coefficient of the sine omega t, and some terms that are the coefficient of cosine omega t. Let me just redo those just in case you may have completely got lost. If you put these in, and I'm not gonna do that by, you just take the second derivative, first derivative, and u itself, put it all here, and you basically arrange them, you come up with something like this, right? You ended up with A times omega n squared minus omega squared times sine omega t minus theta, okay, plus 2 zeta omega n omega cosine omega t minus theta equal to f0 m sine omega t. So on the left-hand side, we expanded these two terms. So we find terms that are the coefficients of sine omega t. What I mean by expanding them, you find the trig identity. So this is like cosine omega t, cosine theta plus sine omega t, sine theta. You expand this. So rearrange all of these, and this is what you got, right? You end up with A times omega n squared minus omega squared cosine theta plus 2 zeta omega n sine theta. This is going to be the coefficient of sine omega t, so it would be equal to the coefficient of sine omega t on the other side, so f0 m. Cosine omega t will have this coefficient, omega n squared minus omega squared, sine theta minus 2 zeta omega n cosine theta. Since there is no cosine omega t on the other side, this is the coefficient of omega t on the left-hand side, this would be 0. So we have two equations and two unknowns. The two unknowns being what? Being A and theta that we want to find, right? So we just multiply this by cosine theta, this by sine theta. If you add them up, these two will cancel out. These two become identical terms, cancel out. Here you have omega n squared minus omega squared times cosine squared, same, times sine theta squared. You add these up, you have cosine squared plus sine squared, which is 1. So you simplify that, and you basically end up with something like this. You get A times omega n squared minus omega squared is equal to F0 over K times omega n squared cosine theta. And you also, in order to find A, so that's what you're trying to do. And then you use another identity, which is this. So you do some algebraic operation, you will see that A will end up being this expression. And you find theta, you see that theta would be the arctangent of 2 zeta r over 1 minus r squared. So in other words, you derive these, and those two unknowns are found. The two unknowns are the amplitude and the phase angle corresponding to this steady state solution. Okay? So you can see that, yes?
I just want to make sure that R is...
The frequency ratio. R is the same as what we had before. R is omega over omega n.
Okay.
Okay? So let's compare this with what we had before. Because this function, these two functions, really lay out the foundation for understanding of many concepts in future, throughout the remaining of the course. If you look at this, let's remind you, okay, that we want to now, this is the solution of the differential equation, right? So that's the math part. Now we need to understand what we have done. So I'm going to call that, those again, observations, or in other words, the interpretation and understanding of what we have derived. Observation number one. Okay. First of all, you can see that this is really the general case of, that includes the special case that was the undamped system. In other words, as you recall, we call this term 1 over 1 minus r squared plus 2 zeta r squared. This is the magnification factor for the case of damped systems. Okay? So let me remind you, when we had an undamped system, we had a magnification factor and then a frequency response function. The frequency response function was this. Okay? And the magnification factor, okay, was basically this. They're the same, basically. We plotted this, right? And this is what the function looked like. Okay? First of all, what is this magnification factor? The amplification or magnification factor. That shows you how the dynamic response is amplified given the frequency ratio. In this case, this was a function of only frequency ratio. And as we plotted it, we realized that this dynamic magnification will be like this, and it increases, goes to infinity, and then starts decreasing, and at square root of 2 becomes again 1. So for the case of undamped system, to simply put it, when this R was less than the square root of 2, dynamic response, the maximum dynamic response, or maximum dynamic displacement, was always greater than the corresponding static displacement, right? when delta, I'm sorry, R is greater than 2, right? U max is less than the corresponding static displacement. Very simple, okay? But let's look what we have here. In this case, this is our magnification factor, okay? If you look at that, the corresponding frequency response function is what? The frequency response function would be a function like this. This we call complex frequency response. This complex function has both the amplitude as well as the phase angle information in it, okay? And what you see here is the magnitude of this function. What do we mean by that, right? If you have a complex number, x plus I, y, magnitude of that complex number, right, is what? Is magnitude of that is square root of, x plus y. This is a complex number, okay? This is x, this is y, this is z, that's what it is, right? So what I'm saying is that if you evaluate z, which is this, that's what you will get. You may not see that directly because this doesn't look like this, but you can make that like that. How do I do that? If you just multiply the numerator and the denominator, if let me call this alpha and this beta, okay? I would multiply this by alpha minus I beta, or the complex conjugate of this, divided by alpha minus I beta. Then what you get is alpha minus I beta, okay, divided by, okay, alpha squared minus beta squared. Because alpha plus I beta times alpha minus I beta would be alpha squared minus beta squared. So this would be alpha divided by alpha squared minus beta squared minus I beta squared over alpha squared minus beta squared. So you see that we turn this function, or this complex number, to a form which looks like x plus I y. Now if you take the square root of x squared, which is, this is x, plus y squared, which is y, is this, you see that you'll get this. So what about that? This one, we're going to plot it and really understand the significance of it. This was the case of the magnification factor for an undamped system. Let's plot now for the damped system, which is represented by that function. And I am going to, as I said, I'm going to call these observations. So observation number 1, okay, which I'm going to continue, is this. Let's plot this function. Observation number 1 is, I'm going to plot this for the special case of zeta is equal to 0. If zeta is equal to 0, you can easily see that these h of r that we were plotting here, okay, will be what? Will be a function identical to what we had before. So the function would look like this. Where this is r square root 2, this is 1, this is 0, this is 1. That means that function is a general case of the frequency response function. If you put zeta equal to 0, you get the case of undamped system. So we discussed this, so we know what the behavior of this looks like. Now, for the case that zeta is not equal to 0, this is what happens. If you plot those functions, you see something like this. That if the damping is small, the peak value of this function is close to r equal to 1. As damping increases, this peak value starts shifting toward left of 1. Something like this. In other words, this is the peak value. The peak value is to the left-hand side of this line. And if, say, this is 0.1, this is point, say, 2, this is, say, 0.4, this is 0.6, the higher the damping ratio goes, the further this peak value shifts to the left of r equal to 1. Not only that, you also see that as you increase damping ratio, you get to a value where zeta is equal to roughly 0.707. That at that point, then the curve would actually fall below this line. And as damping increases, you get curves like this. So in other words, this is, say, for zeta 0.707, 7.1. This is zeta, say 2. This is zeta is equal to 4, and so on. So, in other words, you see a few things. One is, as damping increases, the peak value of this frequency response function is reduced. That means the maximum dynamic displacement becomes smaller and smaller, and once the damping ratio exceeds 0.707, in fact, the dynamic response is always less than the corresponding static response. You can see that, right? Below here, that means that the dynamic response is less than the corresponding static response, because this value, the maximum value, is always less than 1. So what is magic about this 0.707, or how did I figure out that this peak value, first of all, shifts to the left of 1, is never along 1. As zeta increases, it goes further and further toward the left of 1. And then how did I find out that, in fact, for all of these curves for which zeta is 0.707 or larger, their maximum value is 1? Let's clear out. So I would call that observation maybe 3. So first of all, let's find out the maximum value of these curves. How do I find the maximum value of these curves? You have the function, you take the derivative, equate that to 0, right? In other words, what you need to do, you need to take the derivative of h with respect to r and equate that to 0. In order to find the r value for which these curves are maximum. In other words, you find these are values, okay? So let's do that. If you take that derivative, okay, you get this function. You get a function that looks like this. So I'm just gonna write it down for you, okay? So you get something like this. You get, okay, R times 1 minus R squared minus 2 zeta squared divided by 1 minus R squared plus 2 zeta R squared to the power of 3/2. So in order to, okay, of course, in order to evaluate that, obviously, you know, you have, I skipped that a step, but that's what you get. Okay. So this will be 0. This can be 0 when the numerator is 0. The numerator is 0 means 1 minus 2 zeta squared is 0. Either when R is 0 or this is 0, right? So you have two possibilities for this to be maximum, okay? So let's look at R is equal to 0. How do I know at R equal to 0? That corresponds to a maximum or a minimum for those curves. You evaluate the first derivative, or the, you know, take the first derivative, equate that to 0, right? In order to find out if for this value, if this corresponds to maximum or minimum, you need to take the second derivative, right? Or in other words, you take the derivative with respect to R of the HDR, right? You need to do that, okay? If for that R value, this second derivative is negative, okay, that corresponds to maximum point on the curve. If the second derivative, okay, is positive, that corresponds to the minimum value on the curve, right? So let's take the second derivative. What do? Take the second derivative of, you know, the derivative of this. So would be derivative of this minus times that, minus the derivative of the denominator times the numerator, right? But just the derivative of this is derivative of this times that, but the derivative of this times that. So it's going to be a long, long expression. Now I'm not going to go through all the algebra part of it, but I would just write it down, at least the essential part, for you. If you do this, you get a long numerator here, and also long algebraic expression here, okay? If you look at the numerator and set this equal to 0 now, for R equal to 0, which is what we want to find out, for R equal to 0, if this is positive or negative, you will see that you get this value, okay, is 1 minus 2 zeta squared. So for R equal to 0, the value of the second derivative of this is this, okay? Where is R equal to 0? It's right here, right? Right? So look at this. When would this be negative? That means which one of those curves, R equal to 0, is their maximum value. This is going to be less than 0, right? When obviously this is what? Greater than 1, right? In other words, I'm sorry, 1, yeah, 2 zeta squared is greater than 1, or less, that like that, right? So that means zeta squared is greater than, okay, 0.5, or zeta is greater than 0.707. That's what we said for all those curves whose damping ratio is greater than 0.707, they all fall below this line. That is, for these curves, r equal to 0 is their maximum value. Beyond r equal to 0, they just continue to go down, less than 1, okay? So that's for r equal to 0. Now, how about for this case? When we said, okay, we have to take the derivative in order to find out what is the value of that maximum frequency response function, right, at the point of maximum. So now the second option is what? R squared minus 2 zeta squared is equal to 0. This is the second possibility, right? We know that R is always positive, right? Always positive, right? Cannot be negative. This is a ratio of two frequencies. How could that be a negative value? So it's always positive, okay? So therefore, this is what we will get now in this case. That if you equate this to 0, you will get R is equal to 1 minus 2 zeta squared, okay? So R is positive, okay? And what happens? That means zeta is always less than 1, right? So zeta is always less than 1, we know that. 1 minus 2 zeta squared. Since zeta is always less than 1, what does that mean? That means R is always less than 1, right? You can see that. If this is less than 1, the square root of 1 minus something is always less than 1. What does that mean? That means then, for those curves, right? For those curves that you see here, the maximum value always occurs at R less than 1. That's what you said. Isn't that what you didn't say before? That for all of these curves, the peak value is below or before this R equal to 1. Not only that, look at that R. R is 1 minus 2 zeta squared. So the further zeta increases, as long as, of course, is less than 0.707, right? This R value gets smaller and smaller. So the peak value is occurs at R value less than 1, right? And as the damping increases, okay, this R value gets smaller and smaller than 1. That means shifts towards the left, which is what we said before. So that's a mathematical proof of that. That why in the case of undamped systems, okay, as long as the damping ratio is below 707, the maximum value can occur at R equal to 0. Or in other words, for zeta greater than 0.707, the maximum dynamic response is always less than the corresponding static response. And for those damping ratios smaller than 0.707, the maximum value always occurs before the quote-unquote resonance, before R equal to 1. In undamped case, maximum displacement, which was unbound, occurred at R equal to 1. But for the damped system, maximum value of the response always occurs before forcing frequency is equal to the natural frequency. And not only that, this maximum value depends on the damping ratio. The higher the damping ratio, the smaller this maximum value is. So that's really the importance of this curve and really understanding and getting a good grasp of what this means. There's something else that we can also observe, and that is, this is the maximum value, right? In other words, this is this maximum value, okay? Or in other words, this is the R corresponding to the maximum value. In other words, this is the X, we want to find Y. So if this is the R corresponding to the maximum value of that frequency response function, okay, we can actually find the value of this frequency response function at that R is equal to 1 minus 2 zeta squared. So let's see, what is this maximum value, right? If you substitute that in there, in other words, h of R is what? Is 1 over 1 minus R squared plus 4 zeta squared R squared, okay? So you substitute this R in here, okay? What you get something like this, 1 over zeta times 1 minus zeta squared. Okay, that's what you will be getting. So this is the maximum value of the frequency response function. Probably by now you have done a plot of frequency response function in the lab, right? Or is that a good assumption? Have you plotted that, which is something like this, right? One of those curves, right? You must have plotted for a system would be something like this. You've plotted it, right? So let's see what we say. We say that for any system, you can actually find what this maximum value is. This is H max. Zeta is small. For all of these curves, we said that zeta is less than 0.707. So you square 0.7 is what? 0.49, right? So 0.49 compared with 1 is small, right? So if this is smaller than 1, we can make the assumption this is almost equal to 1. It's negligible, right? So in other words, we can approximate this to be 1 over 2 zeta. We assign or a name to this maximum value of frequency response function. We call this peak value Q. You'll see that. In vibration terminologies, this is called a Q. So Q of a vibratory system is 1 over 2 zeta. What does this tell you? If you can measure the Q of a system or the peak value of the frequency response function, you can directly find the damping ratio. Isn't that much easier than that logarithmic decrement that we saw earlier? So that's another benefit of frequency response function. I told you that in the case of damped system, this frequency response function has a lot of applications. We'll see later. But this is the first one of the first important ones. That by measuring the peak value of the frequency response function, you can directly find the damping ratio. Because of this inverse relationship, we call a system that has a high damping, as you can see, the larger this is, the lower that is. The smaller this is, the larger that one is. So a high Q system means a system that is of low damping. A low Q system is a system that has high damping. That's the terminology we use. So if they tell you it's a high Q system, that means its damping is very low. If it's a low Q system, its damping is very large. Yes?
Where did you get the 2 in that equation?
Good observation. This was supposed to have a 2 here. Which I did. Right, good observation. It's actually 1 over 2 times that. Any other questions? Okay. So with that said, we are going to continue with harmonic excitation of dam system because there's a lot more we can learn from harmonic excitation of dam system depending on what is the source of harmonic excitation. So next time we're going to take a look at for us a very important actually problem which we call the rotating unbalance, which is a form of harmonically excited system. Thank you very much. So you get a bonus. We finished earlier than the other class, because I told you.